So welcome everybody, so I'm Muff speaking from Keysight Technology. I want to show you an approach for device modeling to characterization, a complete end-to-end design flow for SIG devices on a half-bridge design, also possible of course for GaN devices and other wide bandgap applications. I want to acknowledge my co-authors as listed here, thank you very much. I want to talk shortly about the used measurement setup, the results in the device characterization, the PCB parasitic effects and how we considered them, and then compare the simulation versus the measurement results. So wide bandgap devices have a lot of applications and the strive for higher performance, faster switching times, better efficiency is unbroken, being in automotive applications for better energy conversion efficiency, let it be in big data centers or photovoltaic systems. But let's say to test if your system is really safe requires accurate models, but where do you get them? It's not only, let's say, what is given in a data sheet. And how can you characterize the different devices and applications, and that is what it's about here in that presentation to give you a solution on hand. Let's say what we can contribute here as Keysight Technologies is basically a complete flow here. You see in 4 steps we have Angelov model for the transistor. You see on the bottom the IEEE reference. We have a double pulse measurement system. We have S-parameter measurements, and we have also a EM analysis, electromagnetic extraction, so basically generating S-parameters of the PCB to improve the models. And basically what you can see here on the left side is that the ringing is not really reflected in the turn on and off switching behavior compared to if we apply these technologies shown here in the middle by IV, CV, S-parameter trace curve, improving the model mathematically, that we can get much better accuracy. I want to show you on this overall flow here now. And so what we use for that one is we call PD1000 software. This is connecting the solutions we have for curve tracer, double pulse test system, VNA, and CV characterization to bring that together into our IC caps power electronics model generator, which can give you the models to a simulation tool, advanced design system, and we do the PCB extraction with integrated PEPro solution here. So what can we achieve here, this conventional method versus the new simulation method? And here you can see that also the timing shifts can be compensated if you consider, for instance, temperature effects and that kind of stuff. And you get a much better match here in more detail shown on the right hand side, also reflecting the ringing. And we have further improved what you can see here, that's deviation on ringing between the simulation and the measurement. We have achieved to become better here in the presentation of that paper. So what we use, for instance, and this is normally not included in the data sheet, just to give you a short intro here, in that presentation format, that we also add CGB, so the gate bias here, measuring the CV characteristic here, and then basically modifying the model respectively. Here you can see such a measurement hardware with different DUT boards for different package types. We have also a heater option to cover the temperature range, I mentioned that, and we can also have by jumpers different gate driver options, so that we drive from 0 to 100 ohm, and we have load inductor options, as you can see here, between 16 and 100 microhenry. Then here a closer picture for the differential probe, for instance. We also use other stuff, high voltage probe, for instance, a thermistor, a coaxial shunt. And of course here it's also very important that you de-embed all these stuff. And here we use the Infinium software we have running on our instruments, and you see here on the right hand side an example between no de-embedding and de-embedding. This is also done for the skews and other effects by the measurement equipment introduced, and let's say by characterizing our probes and putting the S parameters in the de-embed function here, you can get really to the measurement point and the curves you want to see. Here an example for the CV tracing and the fitting. So this is already basically for COSS is ISS and RSS. So the output, the input and the reverse capacitance, the fits and the model results, then basically putting the measurement results into the power electronics model generator. And this is basically here part of accuracy we can achieve. Here on that page, the accuracy achieved on the frequency range up to some gigahertz, basically with the VNA on the different scattering parameters of the device under test, including the board as said, and using the de-embed. So what we do really here, we have the system where we characterize the device on a board. This board itself, the double pulse test board here for the half bridge, was extracted with the 3D EM model generator having an S parameter set, then we put into the simulation. And so we can really consider these effects as well, modeling the control. So this is clear, so the gate driver basically, and then this extracted device model we can then feed back to the simulation, to the transistor models, as well as we do with the extracted board model. And this is basically a flow what you can do on every implementation. So you just replace the double pulse test board by your application board and rerun the simulation, and so you can directly see the effect of the implementation chosen by any application design. So the EM extraction, which was, let's say, in previous times more for experts, became very, very easy. You have a drag and drop solution to define the ports in terms you drag the components, tell the pins, and in the schematic they are automatically recognized. So you enter the switching frequency, rise and fall time, and then you simulate and back annotate by just pressing generate a schematic representation of the results. Here you see the results. So basically here I've chosen to stick to the 10 minutes, a 10 ohm gate resistor. On the left hand side you can see the improved model, on the right hand side you can see the original model from the vendor offered. And here basically you see the ringing is not really reflected in the upper right on the green one, and on the lower right even the pulse width is not correct. On the left hand side the ringing is much better, as well as the pulse width. So the accuracy is really improved here by a closer characterization based on the Angelov model for that SIG switching device. Layout effects, last but not least, you can see here if you simulate without a layout, and then you see the measurement and the comparison with the layout extracted, you see a much better accuracy. The frequency of the ripple is maybe not right. Some parasitic inductances modulating that ringing, I would say, which are not there, maybe in the measurement setup itself, what was not de-embedded. And so, but from the rise and fall time here in the ringing, you see much effect of the layout, and of course this can determine the efficiency of your application. Concluding up in the 10 minutes, the demonstrated modeling solution reflects influence of parasitic effects and how to better predict the switching behavior, the ringing down, over undershoot of your device and your implementation. The demonstrated design flow is really accurate, and if you can generate such an accurate model, you can really use it on any arbitrary application board to verify your performance just by exchanging the PCB model. And so the EM extraction does not require much expertise anymore, because it's a very, very easy defined flow where we offer also conducted and radiated EMI test benches. Thank you very much, and welcome to the Q&A session.